Hi, how are you doing? I am Mohammad Sadri, postdoctoral researcher at Microelectronic Systems Design Research Group, TU Kaiserslautern, and this is one of our educational ZYNQ training videos, and it is titled AXI Interfaces. Since AXI interfaces in the ZYNQ device are of a very high level of importance, we have dedicated several videos just to talk about the AXI interfaces of inside the ZYNQ device, specifically the AXI interfaces through which the PS and the PL talk to each other. And we will describe each of these interfaces in detail, and we will talk about how someone can use them to transfer data between the PS and the PL inside the Xilinx ZYNQ device. So here is the block diagram that we saw together in previous videos. It is an overall brief block diagram of the Xilinx ZYNQ device. And as we described, and as the block diagram shows, the ZYNQ architecture is divided into two parts: the programmable logic and the programmable system. And today, what we are going to begin to talk about are these interfaces. In fact, the interfaces which allow you to transfer the data from the FPGA part of the Xilinx ZYNQ device to the CPU part of the Xilinx ZYNQ device, and vice versa. Before going into further details, let's make sure that we briefly know what is AXI and what is an AXI interface, what is an AXI master, and what is an AXI slave. First, in today's world, as you can see, we have chips containing a large number of different types of IP blocks. And these IP blocks need to talk to each other, need to transfer data between each other. Towards this, we need a kind of a standard based on which all of these IP blocks can talk to each other. So every IP block cannot introduce its own way of talking to the outside world. All of the IP blocks that everybody designs should obey one specific set of rules for receiving data from outside world and transferring data to the outside world. Towards this, we have seen several standards appearing in the design community by big companies to solve this problem. AXI is one of them. Very basically, AXI is a kind of method, is an standard through which different components inside your multi-component chip can talk to each other. Every AXI link contains necessarily two parts: one AXI master and another AXI slave. The AXI master is the one who initiates transactions. It begins read or write transactions. The AXI slave is the one who responds to the transactions initiated by the AXI master. The transactions can be either read or write. They are always initiated by the AXI master. However, for the read transactions, we have the data flowing from the AXI slave toward the AXI master. For the write transaction, we have the data flowing from the AXI master towards the AXI slave. In both of the cases, the one who is initiating and beginning the transaction is the AXI master. But for reads and writes, we have different data directions. Now, we have two types of AXI interfaces: AXI memory mapped interfaces and AXI stream interfaces. The AXI stream interface is basically a reduced or very simplified version of AXI memory mapped interface. If we try to look in more detail at one AXI memory mapped connection, what shall we see? We see different set of signals for read transactions and another set of signals for write transactions. For read transactions, we basically have these two groups of signals involved. First, when the AXI master wants to initiate a read transaction to an AXI slave, it needs first to provide the slave with the address from which it wants to perform the read operation. So basically, we will see that there are a set of signals that we call read address channel going from AXI master to the AXI slave. In fact, there are a set of signals between AXI master and AXI slave dedicated to transfer the read address to the AXI slave. Then, the AXI slave answers with the required data to the AXI master. So, we have a read data channel. Through the read data channel, the data in the specified address by the AXI master will be transferred to the AXI master, to the requesting component. Then, for write transactions, again we have another set of signals. First, obviously, the AXI master needs to provide the AXI slave with the required write address. Second, the AXI master should send the data that it wants to be written to the specific address at the slave side to the AXI slave. And third, the AXI slave should respond to the AXI master if the data is transferred correctly, is written correctly or not. So we have a write response channel. Each memory mapped AXI interface or each memory mapped AXI connection has these 5 channels. Now, let's have a look at what is the contents, what is the internal signals of one of these channels in slightly more detail. So, I take the write data channel and I go and have a more detailed look at the contents of this channel. If we look, we can see that the basic signals that are creating each channel are the following. First, from the AXI slave, there is a ready signal coming to the AXI master. This ready signal is indicating to the AXI master that, hey, I am ready, you can begin your operation. You can begin transferring the data. Second, the AXI master sends a valid signal to the AXI slave indicating that the data that I am sending to you is now a valid data. So, whenever the AXI master is transferring a valid data to the AXI slave, it also enables the valid signal. Practically, these 3 signals are the main signals which create each of these AXI channels. There are other set of signals inside each AXI channel as well. For example, each time that you want to transfer a set of data, you indicate the size of the data or the width of the data which is being transferred. You can transfer data in single beats each time, for example, 1 word of data or 1 byte of data, 16 bits of data. Or you can transfer data in bursts. Each time you can transfer, for example, 256 bits of data continuously without interruption. Then in that case, we need the burst length. And then sometimes for a specific set of data that you want to transfer between one AXI master and the slave interfaces, you need some quality of service measures. For example, some set of data are more important than the rest of the others, and you need to somehow indicate this. Then we have a set of QoS signals passing from the AXI master to the AXI slave indicating these points. There are also a set of custom signals that the user can drive them by its own wish. In fact, the programmer, the hardware designer can decide what he wants to transfer on this set of signals. But the three signals that I'm showing you here are the main signals building each of the channels. Now, in addition to AXI memory mapped interfaces, we have also AXI stream interfaces or AXI stream connections. In many cases, in the hardwares that we implement on ASICs, on FPGAs, and different types of logic, we have blocks that receive the data, perform a kind of processing on the data, and then pass the data to the next step. For example, the data is coming from an A to D, and the data goes into a filter, and then the data gets passed to the next module. We have the stream of data flowing inside our hardware. In these cases, when a module wants to transfer data to another module, it doesn't need to provide the address for that specific amount of data. And furthermore, the direction of data is always unique. The direction is always from this module to the next module. It does never happen that you need to transfer data from this module to this module. So practically, what is happening, this module in an AXI stream interface is always writing to that module. And no address for these data transfers are required. This builds the principles of AXI stream interfaces. And basically, if you look at one AXI stream interface, you can see that it's the right channel. So if I look at one AXI memory mapped interface and I extract its right channel and I look at its signals, basically you are seeing an AXI stream interface. So again, the important signals which create an AXI stream interface are the followings: the ready signal from the slave to the master, and the valid and data signal from the master to the slave. Look at this naming convention. For all of the streaming components, the name of the ports usually begin with AXI S. Then if the port is a slave port, we have underline S. And if the port is a master port, we have underline M. For all of the memory mapped interfaces, the name of the port begins usually with AXI. AXI underline the rest of the name. For AXI streaming interfaces, it begins with AXI S underline the rest of the name. You will see as we progress through our training videos, you will see that this naming standard is obeyed in most of the blocks and modules that we will use for our designs. Now, having these definitions for AXI interfaces in mind, we will go ahead and have a relook at the architecture, at the structure of the Xilinx ZYNQ device. Now let's go back to the architecture that we were showing for the Xilinx ZYNQ and have a more detailed look at the AXI interfaces that we have between the PS and the PL. So we are going to focus only and only on these AXI interfaces, and first, at the first stage, I want to have a look at these ports here. HP0, HP1, HP2, HP3, which we call high performance AXI interfaces. These high performance AXI interfaces are slaves for the logic that you develop inside the PL. So practically, they are AXI slave ports of the PS. All of the ports here, as I described before, they are memory mapped ports. There is no streaming port here, and in future videos I will describe to you what you should do to translate one stream AXI interfaces to one memory mapped AXI interface. But let's for now focus on these AXI memory mapped interfaces. And here, for these HP ports, we have each of the ports with a width of 64 bits. The logic, the hardware accelerator, and the block that you develop here should contain AXI master block or AXI master interface, and through this AXI master interface you can get connected to this AXI slave port, and this AXI slave port redirects you to the address space of the PS. So the logic that you have here can initiate read and write transactions to the DRAM memory that you have here, or to the OCM, to the on-chip memory that you have here. Then, we have these two AXI master ports. They are called MGP0 and MGP1. The widths for each of the ports is 32 bits. And these ports are practically very important because they are the only master ports of the PS. So these ports are master ports of the PS, meaning that I need to, in fact, develop AXI slave interfaces or AXI slave plugs for my modules that I implement on the PL, so that the logic that I have in the PS can transfer data to the logic that I have in the PL. Through these AXI interfaces, for example, the CPU cores that you have here, the ARM CPU cores, can initiate read and write transactions to the logic that you have implemented on the PL. So whenever the ARM CPU core that you have here initiates a read or write transaction to a specific address range that I will show you later, then the transaction will be appear on these two AXI master ports, and then it will be transferred to the AXI slave plugs that you have developed on the PL, and then your logic on the PL should provide the suitable response, and the data through these AXI master ports will then be transferred to your CPU cores. These two ports are the main means of your ARM host to control the hardware that you have developed on the PL. So they are very important. Furthermore, these two ports are the main means of the DMA engine that you have here on the PS to perform reads and writes to the logic that you have developed on the PL part of the ZYNQ. So these two AXI master ports are very important, and they allow your CPU cores to initiate read and write transactions to the blocks that you create on the PL. Next, we have the accelerator coherency port. The accelerator coherency port is very similar to the HP ports. The width is 64 bits. It is an AXI slave port for the PS, And thus, we need to develop AXI master plugs and connect AXI master plugs to this ACP port so that we can initiate read and write transactions to the PS. The main difference of ACP port compared to HP port is that, as you can see, the ACP port gets directly connected to the ZYNQ control unit. And the ZYNQ control unit is connected to the caches of the CPU, the L1 cache and L2 cache. So whenever a transaction is initiated by the master that you have here, then first the caches of the CPU will be checked for that data. Indeed, the caches will be searched for that specific physical address of the transaction that you have initiated. And if the data is available, if an instance of the data is available, then maybe if all of the conditions are met, the transaction will be responded by the data in the caches. This allows faster data transfers and more energy efficient data transfers from the ARM subsystem to the hardware accelerator or to the logic that you have developed on the PL. If for the AXI transaction which has been initiated on the AXI master, there is no correspondence, copy, or data or instance inside the caches, then what happens is that through this port, the transaction will be redirected to the DRAM memory. And from there, it will be responded, it will be answered by the data stored in the DRAM memory. This, of course, introduces an additional latency, which may degrade the performance of your system. As we will see in future videos, using the ACP port should be done with extreme caution. Whenever you have a kind of task in which you want your ARM host CPU to collaborate, to cooperate with a hardware accelerator implemented on the PL, then the ACP port that you have here can be an extremely useful mean. This means that they can use, these two components can use the ACP port and in fact the caches of the CPU for sharing data. This allows the ARM host and the accelerator to share data very fast with low energy consumption. But as I will show you in future videos, if you don't design your structure and your algorithm and memory allocation very well or efficiently, then this may not only improve your performance, it can decrease, in fact, runtime, and it can increase runtime, and it can increase energy consumption. Finally, we have these slave general purpose ports here. And again, these are slave ports for the PS. So in the PL, you need to develop AXI master logic, and the AXI master logic will drive transactions through these general purpose slave ports, in fact, to the peripheral and different components inside the PS. Again, these ports are each one 32 bits. Okay, now I want to have a more detailed look at the architecture, internal architecture of the PS, and how each of these AXI plugs is connected to the rest of the components inside the PS. For this purpose, I use the ZYNQ Technical Reference Manual document, which is coded as UG 585 in the Xilinx website, and you can download it very easily. Indeed, it is the most complete reference for the Xilinx ZYNQ and the ZYNQ architecture. So, we go ahead with a system level view of the ZYNQ device. First, At the top, we have the PL fabric. And as you can see in the PL fabric, we have first high performance AXI controllers. Then we have cache coherence ACP port. Indeed, the AXI controller which will be connected to cache coherence ACP port. And then we have general purpose AXI masters. These are the guys who will drive SGP0 and SGP1 port. And then finally we have general purpose AXI slave ports. These are the hardware logic that we develop and will be driven by GP1 and GP0 AXI master ports. I begin here and I go down through the architecture and I try to track each of these signals to see where does the signals go and to where they get connected. So what I have here, in fact, is a set of AXI master plugs. These AXI master plugs are implemented inside my logic, the logic that I have developed and I have implemented inside the PL of the ZYNQ. And then these AXI master plugs, they are connected to the AXI slave ports, indeed HP0 to HP3 ports of the PS, and then they go inside the PS. So first, they are passing an async block, meaning that the clock domain can be changed. In fact, the clock which is driving the rest of the logic here is not necessarily the same clock that is driving this AXI interface here. Then we have a FIFO, which can buffer the data and the transactions, the data related to transactions which are passing, which can result in an improved performance. Then, finally, we have a kind of AXI interconnect. We have an interconnect through which different ports, which are coming, in fact, from the HP0 to HP3 plugs, will be connected to the rest of the architecture. Now, let's scroll this map a little bit down and see what will happen to these signals. So, as you can see, at the next step, after this AXI interconnect that we have here, in fact, we have 3 ports. 2 ports, each of them 64 bits, and then another port. And practically, I would say all of these guys can access, I would say, each of these ports here. And then we have this component here, which is called OCM interconnect, on-chip memory interconnect. And if I follow this component later, you will see that is connected to the on-chip memory. And the interconnect is driven by first this AXI HP interconnect, meaning that every module that you have connected to each of the HP0 to HP3 port can, through this OCM interconnect, can access the OCM. And furthermore, as we will see, the rest of the components inside the system have also the possibility of accessing the OCM. So let's scroll down the map a little bit more and see what will happen to these 2 signals here. If I go down slightly, I can see that these 2 signals will go to the DDR controller. Indeed, they are going to the DRAM memory. So the AXI masters that you have implemented on the PL and have connected to the PS through each of the HP0 to HP3 ports, they have the possibility of directly accessing the DRAM memory, writing data to DRAM memory and reading data from it. Then, if I look, I can see that my ARM CPU host, which is here, has also the possibility of accessing the DRAM memory. So we have our CPU host here, then it has its own caches, then we have the Snoop control unit, then we have L2 cache, and then we have this M0 port, and if we follow the M0 port through an async block, it will go to the DRAM memory. So, the AXI masters that we implement on the PO and we connect to each of the HP0 to HP3 port can share the data with the CPU over the DRAM memory. They will access the data through these two ports, and the CPU is able to access the data through this port. Now, let's get back again to the top of the map and see to where the accelerator coherency port is connected. Here, we have, in fact, an AXI master plug that we have implemented on the ZYNQ PO, and this AXI master plug is connected to the accelerator coherency port, to the ACP port. And then, through an async block, it is directly connected to the Snoop control unit. And then the Snoop control unit is connected to the L2 cache, or generally speaking, the caches of the CPU. This allows the AXI plug that you have here to perform coherent transactions to the memory space of the CPU. And if the data instance is available here on the L2 caches or the caches of the CPU, the transaction will be responded directly with the data available here. The Snoop control unit, as you can see, has two ports. One port is going to the level 2 cache, to the level 2 shared cache of the ARM hosts. And then another port, if we follow, we can see that it will go to the OCM memory. So, the AXI master that we have implemented on the PO and is connected to the ACP port can, through the Snoop control unit, go to the on-chip memory. If we follow, we can see this fact. Here, we have the Snoop control unit, we have the on-chip RAM, in fact 256 kilobytes, and it has two ports. One port is directly connected to the Snoop control unit, and another port is connected to the OCM interconnect. And the OCM interconnect, as I described to you, can be driven by each of the HP0 to HP3 ports, and also the rest of the components which are available inside the ZYNQ PS. Then, if we look at the level 2 cache of the ARM subsystem, we can see that the level 2 cache has two ports. One port, as we described, goes directly to the DRAM. And the other port, if we follow, we can see that it goes to a slave interconnect. It's called a slave interconnect. So I have the port of the level 2 cache, and it is coming and is getting connected to the slave interconnect. And this slave interconnect has 4 AXI master ports, as you can see, M0 to M3 here. And each of these AXI master ports will be connected to the part of the system. So, through this interface, the ARM host that you have and it's running on the system can access each of the peripherals that it wants. As I described to you, the ZYNQ device provides a set of peripherals to the user, such as, for example, SD card interface, USB interface, network interface, and all of these interfaces can be accessed by the CPU through this interface, through this port. Furthermore, we have a DMA, in fact, we have a kind of central, I would call central DMA controller here, which can be programmed by the CPU, and this DMA controller can also perform some transactions and data transfers for us. The DMA controller is a master for this central interconnect, and if we follow the slave ports of the central interconnect, we can see that one of them, if we follow it, goes to the OCM interconnect, and the other one, if we follow it, it goes to the DRAM, and the other one, if we follow, it goes to the slave interconnect. Finally, if I look at M0 and M1 ports that I have here, if I follow these two signals, I will see that they reach, in fact, these two interfaces here, which are practically the GP0 and the GP1 ports of the PS. And these two master, AXI master ports, they can get connected to the slaves, to the AXI slaves that I will implement on the ZYNQ PL. Okay? So on the ZYNQ PL, I create hardware containing AXI slave blocks, and these AXI slave blocks can get connected to GP1 and GP0 port, and practically, as I showed you, these two ports are driven through the slave interconnect. And since the slave interconnect is driven by the CPU, by the DMA, and by the peripherals, each of them also can have access to the logic that you develop in the PL through these ports. Okay, don't worry if this looks confusing to you. Practically, the goal was to have a more detailed overview of the internal architecture. And for actually designing systems with the ZYNQ, you don't really need to know everything in detail. It's absolutely not necessary. And having a very rough knowledge of what are these ports, what are these AXI ports, and how I should connect and where I should connect the hardware that I have developed in the PL, this is completely enough. Okay, obviously, this, in fact, CPU system that we described in the PS, it has a memory map. And each component in this system will contain an address range. For example, you may ask me, how shall I initiate transactions to the GP0 and GP1 port? Suppose that I want to write a program running on the ARM host, and inside this program, I want to read a piece of data or write data to the GP0 and GP1 port. How shall I do that? The answer is here in this table, the address map of the device. And inside this table, you can see that every component in the system has a specifically defined address range. In the next video, I will describe this address map in more detail, and we will see in more detail how, through programming the ARM host, we can access each of the, in fact, GP0, GP1 port, and consequently the hardware that we implement on the PL. This is the end of the current video. Thanks for watching, and we will meet you in our future videos.